So power is not energy, right? Power is energy over a defined period of time. So for instance, we have a joule, right? We know what a joule is because of the force times distance and the ability to heat up water. But if we want to know about what's the power of something, what's its capacity, we want to know over what period of time. So a joule per second is a watt. And we have to get familiar with BTUs. If you look up energy statistics on this country, you're going to find it in quadrillion BTUs. If you buy an air conditioner, the rating is going to be in BTU hours. So we just have to live in this environment. So, for example, a ton of refrigeration is 12,000 BTU hours. So people talk about a 2-ton refrigeration system. Anyone know where that idea of a ton of refrigeration comes from? Why a ton? Any idea? Why is it weight? Yeah. Precisely. A ton of ice has about 12,000 BTUs of latent energy absorption capacity. And so the Empire State Building actually used to be entirely cooled by ice from New Hampshire. They would harvest the ice off ponds, cart it down to New York, load it in the Empire State Building, and had big fans that would cycle over the ice, and that was the cooling system. And not long ago, they figured out that actually they could reactivate that system, make ice at night when electricity was cheap in the Empire State Building. So, anyway, so a kilowatt hour, that's most, like electric bills are going to come in kilowatt hours. But for a power unit like that, it's a kilowatt hour per hour, right? So you cancel out the hours, so that's a kilowatt. Same as here, it's a power unit. And then we had a foot-pound, right? Because we came up with that before. That's the same idea. And a foot-pound is related to a horsepower. So it's basically 550 foot-pounds per second. So when people talk about horsepower, that's what we're talking about. And obviously that's going to be related to what they thought a horse could pull. How many pounds you can pull per foot. Is growing a lot, right? So you've got all these fuels, and this graph doesn't stack them. So you can see that the actual energy use of the U.S. is kind of growing exponentially. It's, much more dramatic than this chart. But you also see that for dates where we have the measure of gross domestic product, which is a measure of all our economic activity, and it's certainly questionable, but it's roughly, it's good enough to think about anyway. It's growing even faster than population. It's growing roughly in concert with the energy use. So we had a biofuels-based society, with a much, much smaller population. With this type of population, probably we don't have the land area to do biofuels. Which gets us back to this Sankey diagram, where we see here's the amount of biomass that was put into the energy system, mostly going into the industrial system, a little bit, say wood fuel, pellet fuel, etc., and a little bit into transportation as ethanol, but not nearly the 15% blend rate that's required, right? So we've got this map where we're dominated by the fossil fuels. And the reason I wanted to have you do that calculation was, one, to mess around with units and get used to transforming these quantities, but also to kind of think about, again, you know how much you weigh and how fast you can run up things, so you should now have a sense about your own high burst power and what that, how that relates to when we talk about the power of an air conditioner. So I think we said that Kevin's high burst power was something like 700 watts, I think. cheap air conditioner, window air conditioner might be what would that be? About it could run. Actually, it's probably not a good example. A toaster. A toaster will also draw about that same power. Nice to think of yourself as a toaster. Huh? So the other thing to think about is how to solve time. So I want to get back to electricity generation, because the other thing we had was that this biofuels-based system, where we're feeding humans to do work for us, instead of these fossil fuel slaves, when we're thinking about that as a metaphor, they weren't very efficient, were they, right? They required 80 watts just to stay alive, and then you only got 40 more watts of power, right? So not a terribly efficient machine. Actually, relatively efficient, because here's electricity generation, where you get 12 quadrillion BTUs out of the power generation industry, but you've got 26 quadrillion BTUs of waste. So it's also not very efficient. And we talked about this last time, and I just want to, so for instance, if you have an electric space heater, how many people used electric space heaters, right? Turn it on, makes heat for you. Does anyone know the efficiency of an electric space heater? Is it terrible? What would you guess?
The efficiency?
Yeah.
Like when it's plugged to the wall?
Yeah. At the wall. Like if you're buying a kilowatt hour of electricity from the utility, what amount of heat in kilowatt hours are you getting out?
Like into the room, right?
Yeah, into the room.
I'd say maybe less than 5%.
5%, you think?
Less.
Less than 5%. Anyone else got another guess? How about 99 point something percent? That's efficiency. That's efficiency at like where you plugged it in. What you're getting at, you're a little extreme. It's a little better than what you described. What you're getting at is the system efficiency, right? Where the coal that you put into the power plant, that you use to boil the water, to turn the turbine, the friction loss, every single one of these transformations, right? You're losing energy to each transformation. So you boil the water, you turn the turbine, you transform it, you boost the voltage, you turn it to alternating current, you send it down the wires are humming, and that humming, well, that sound and that heat off that wires is attenuation, about 10%. That leaves and it gets to your house, and you get 100% efficiency on your electric heater. But the whole system efficiency is much, much less, probably more like 30%. Or 20%. It depends, we're going to get into this, it depends on where you are and the efficiency of the grid and the fuel sources for the grid. So that is the difference between primary and site energy. So primary energy is the amount of energy in the coal, okay? Site energy is the energy that gets into your electric heater when you plug it into the wall, all right? So I took this off of the Energy Information Administration, and this is for site energy by different end uses, right? So you look at space heating, and it's certainly the big Megillah for U.S. houses right now. And I'd like to argue that actually it really shouldn't be, even from a site energy point of view. We can do amazing things with heating if we make our buildings good. But you'll see water heating is fairly big. Space cooling isn't really that big compared to heating and water. But when we look at primary energy, now we've got different multipliers, right? So because the fuel going into most heating systems is not electricity, you get, say, fuel oil, and you combust it on site. And let's say you combust it at about 80% efficiency. Well, that's better than 25% efficiency. So if you burn your fuel oil in a diesel generator and sent it down, that's where you'd be losing all that efficiency. So now, even though it's still not 100%, so this number is still larger than this number, it's a smaller percentage because now all of these electrical uses like space cooling and pretty much all your other uses except for water heating are all electricity, so you have to multiply them by this grid factor, by whatever the inefficiency of the entire grid system is from generation to your plug. So what are the implications for that? Here, this is another way of thinking about it, where you can kind of compare them side by side. So space heating is still a big deal, but it's relatively, it doesn't grow as much when you multiply it by the efficiency to get back to the primary energy. Whereas space cooling, much, much bigger deal. So that you might look at the differences in the way you calculate this for regions. If you look at the Northeast, if you look at site energy, we and the Midwest are pretty bad, and the South and the West are pretty good. Right? They use less. But if you look at source energy, which takes into account the grid and what they're actually using, well, in the South they're doing a lot of air conditioning. So essentially multiply their biggest energy use by 3. And that makes a big difference. And so this makes a difference in terms of policy, right? It makes a difference in terms of, if you look at it from site energy, we're above the national average by about 16%, and the South is below the national average by 10%. And the West is actually pretty good because they are lucky. But also they have a better grid, different grid sources. They have a lot of hydroelectricity and a lot more natural gas burning than the other parts of the country, so their grid factor is less. But then if you multiply this by source energy, all of a sudden we're better than the average by 5%, and the South is worse than the average by 11%. So taking site versus source makes a big difference. And this is not only be different, say, from the point of view of what regions are worth paying attention to if you're going to make policy or you're going to invest in energy efficiency technologies. It also makes a difference when you're trying to think about, say, building a net zero energy house, just one building. If I want it to produce as much energy, say, with photovoltaics as it's consuming overall, I have to think about the site production of the energy and the energy that's coming in that's not in the form of electricity that I generate. And what about my use of the grid, right? Because people, and we'll get into this with PV, grid-connected PV is sending electricity to the grid when you're not using it, and then you're drawing electricity from the grid when you are. Well, which one do you account for and when? It becomes kind of complicated. But the important story here, I think, is about carbon dioxide emissions from buildings. Our fossil emissions have flattened, which is to say we've done a lot of things right in reducing our use of fossil fuel by making our buildings better. But our overall energy picture is still getting worse because we're using more and more electricity because of other stuff. So we're going to talk about that next time.